And in this class, we will be discussing about fission reactors. So first we will consider the reaction one more time, a little bit in detail, and then we'll go to the nuclear reactors. We are focusing on that fission reactors. Okay. So we'll start from some basics. So if you consider that nuclear reaction that we just discussed in the last class for uranium-238 and uranium-235. So the expression was like this: when a thermal neutron, that is energy of these neutrons will be very less in the thermal energy range, few electron volts. Okay, so then that is absorbed by this uranium-235, and this undergoes that excited state uranium-236. Okay, and then this will undergo to those daughter nuclei X plus Y, and some numbers, few numbers of neutrons again. So this new numbers of neutrons, and we discussed this how these neutrons are coming, all those things in the last class. Okay, so these neutrons are important when you consider that nuclear reactors. So when you consider this kind of reactions, then we can easily say that this neutron energy depends on this kind of nuclear reaction, because if this neutron, if there is no energy for this neutron, for example, if you consider uranium-238, if these neutrons are in the thermal energy regime, which means that these neutrons are thermal neutrons with a low energy, such neutrons cannot produce fusion with the uranium-238. So if you increase this kinetic energy of these neutrons, the probability of fission reaction will be larger, theoretically, I'm saying. Okay, so because when you consider that activation energy, all these things, and that Q value, so if you consider that graph, I'm just roughly drawing here, so it will be like this somewhat, okay, somewhat like this. It will be going like this, 1 by r form. So this is that this is not the exact curve, but I will just draw it like, it will be like almost like this. Okay. So just consider it should go like this, and suddenly it should. So this energy, that is the activation energy, that has to be overcome by the nucleus. Okay, so this if the incoming neutron is having enough energy, if it is not in the thermal energy, if it is having more kinetic energy, and that kinetic energy will be transferred into this excited energy nuclei, okay, in the excited state, so the total energy will be increased for this excited nucleus, because the neutron itself already having some kinetic energy, and that neutron is absorbed, so that this excited nuclei, which is 236 uranium, that will be having more energy, and it can easily overcome that potential barrier or this activation energy. So conventionally we can say that this neutron, if it is having, this neutron is having more energy, then the probability for the fission will be higher. Okay, that is theoretical or conventional way of thinking, but in experimental, or you can say that when you calculate that probability, this is not the case. Okay, because when you increase the kinetic energy, When you increase that kinetic energy of incoming these neutrons, and the cross section of the fission cross section, that is going to be decreased, which means that the probability, fission cross section means nothing but fission probability is going to be decreased. Okay, so for that we have to look into this curve here. I don't know, it is somewhat visible. This curve I have to check this curve. I hope it is not that much visible, but somewhat. Okay, and this one. So I will just take another color for this. Okay, and in this axis we have that cross section. I'll just write here cross section. This one is not cross section. Sigma in bonds. So this is in this axis. This is y-axis. This is cross section. You can write this as fission cross section. Here we have in x-axis this one. This is nothing but the kinetic energy of that neutrons. You can simply write the energy of that neutrons, because sometimes when you consider that thermal energy, so I will just erase this energy of that incoming neutrons. Energy of neutrons. This side you have that logarithmic scale value. So this is 10 to the power minus 2. This is 10 to the power minus 1. And this is 1. This is 10, 10, 1, 10 to the power square. Square. 10 to the power 3, 10 to the power 4, 10 to the power 5, 10 to the power 6. So both the scales, both axes, you have a logarithmic scale. So this is 10 raised to minus 2, minus 1, 1, 10, 10 square, 10 cube, 10 raised to 4, like that. So it is logarithmic value. So the scale is in logarithmic value. So because when you have 100 here, 10 square is 100. You have 10 here. So in between these two, there is a 10 division. There are 10 divisions. Sorry, from 10 to 100 division is not required. So there will be 10 division, like so from 10 to 100 if you consider. But when you consider from here to this 10 cube, from this will be from 100 to 1000. So the number of divisions same, but the divisions having different values from 10 to 10 to 100 and 100 to 1000. So each division will be having different values. So I don't know whether you know those things. I will just show here. For example, if you consider that this will be 10, okay, then next is 10 square, that is 100, then you have 1000. So let's consider this in between these two there is there are 10 divisions, so it will be varying from 10 to 100. Okay, which means that 10, 20 like that. So it will be up to 100. So when it consider here, same division, number of divisions are same, but here it will be 200. So in between these two, there is 100 difference, but when you consider these two, there will be only 10 difference. So it is logarithmic scale. So these divisions will be different from in that axis. So it is in logarithmic scale. Okay, so it will be having very high value when it reaches around 10 raised to 7, etc. So that you can fix that along with the 10 raised to 2, 10 raised to 1, all those values when you express that scale in logarithmic. Okay, so just look into that if you don't know that. Okay, whatever it is. So here we have that this is in logarithmic scale, and this is in again logarithmic scale. So here it is 10 raised to minus 3, minus 2, minus 1, 1, 10, 10 square, 10 cube, 10 raised to 4, like that. This is the fission cross section in bonds. This we already discussed the unit. I hope you know that. In this scattering cross section, we already discussed this bond, and one bond equal to 10 raised to minus 28 centimeter square. So that is the unit of cross section in centimeter square. So that we already discussed when we did that Rutherford scattering experiment. Okay, so that is in that y-axis. In here it is fission cross section. So this will give you that probability of fission. That fission cross section is nothing but your probability of fission. That is in the y-axis. Now in x-axis we have this energy of neutrons. Okay. Now you can see this graph is decreasing, having some decreasing trend. Even though here we have some kind of fluctuations from that straight line. Okay. We can say that these are the resonance. We have some up and down resonance peaks. Okay, so this graph shows that when you increase the energy of neutron, here you can see this is the energy of neutrons in the x-axis. So when you go from 10 raised to minus 2, 10 raised to minus 1, 10 raised to 1, etc. So when you increase your x-axis along this x-axis, when you increase that energy of incoming neutrons, that cross section is decreasing. You can see here this cross section. It is almost like this. I will just draw it to then you can see it a little more clear. So there is some up and down here, some fluctuation, some resonance. Then when it reaches here again, it is coming like this. So this is a curve or graph for uranium 235. This is for uranium 235. 235. Okay, this is uranium 235. This graph. So what is the conclusion? The conclusion is that when you increase that incoming neutron energy, your fission cross section is decreasing. Your fission cross section is decreasing, which means that the probability of the neutron to get absorbed by that nucleus is getting reduced when you increase that neutron energy. So if you consider around 10 raised to minus 2, 10 raised to minus 1 thermal energy, that is in the thermal energy, few electron volt only. So that means this region. I'm talking about this region. So in this region, we have very small energy that which is having 10 raised to minus 2, 10 raised to minus 1, few electron volt, and which will be in that thermal energy range. Normally that thermal energy will be coming around 0.25 electron volt, etc. So these neutrons which are in this part, okay, in this part, they are having around some 10 raised to minus 2, 10 raised to minus 1 electron volt of energy. That is some point 1.2, 0.3, etc. Those range of energy will be there. So they are having very low energy. These neutrons are, we call it as thermal neutrons. Okay, so in here the cross section you can see, which is around 10 raised to 3, and this is coming, if you can take this average value of this is around some 7, sorry, 600 or something. So let's say this is around 580 bonds. Okay, so that is here it is 100, here it is 100. So when you take this range between these two, so it will be around some on an average we can say 580 bond. Midpoint of this will be around 580 bond. So this is the fission cross section that is available when you have this uranium-235. When the neutron is having a range of energy which is around 10 raised to minus 2, 10 raised to 1, and in that range. Okay, you can see from here that this range I am saying. So these neutrons are thermal neutrons, which are having some point, 0.1, 0.2, 0.3 like that of electron volt energy. So these are thermal neutrons. Okay, so around they will be having around the fission cross section around 580 bonds. Now you consider the second regime where you have that resonance, means that there is a fluctuation. You can see here this fluctuation. In this fluctuation regime, we have that average behavior still decreasing. Okay, that the scattering, sorry, fission cross section is decreasing along with the neutron energy. So this region we call it as resonance region. Resonance region. How can I say resonance region also? Okay. So resonance region where you have this up and down. Okay, it is not a very smooth curve. It is not a continuously decreasing curve, but there is on average we can say that it is decreasing. On an average, it is having some showing some average decreasing value. So it is going up and down, and this particular region, which is showing that up and down action of the cross section, fission cross section, which is called as resonance region. Okay. Then we have another region, which is this part you can see. So this is around up to this 10 raised to minus 6. You can see 10 raised to minus, sorry, 10 raised to 6 range. So 10 raised to 6 means 10 raised to 6 electron volt, which means that 1 mega electron volt range. So for that we have almost less than 1. Okay. So it is almost less than 1 and 10 raised to minus 1. In that range it will come. That cross section I'm saying. So if you see that, so this is almost less than 1, this scattering cross section. Sorry, this fission cross section. So the fission cross section is very small when you consider the mega electron volt neutrons for uranium-235. Okay, I hope you understood this. So in this region, you can see that the fission cross section is around this 1 and 10 raised to minus 1 range. So it is very small, and the energy of neutron in this region is in the mega electron volt range. Okay, so in mega electron volt range, or when the neutron is having very high energy, the fission cross section get reduced. That is the probability to get absorbed by the nucleus. These neutrons, the probability of these neutrons get absorbed by this nucleus will be less when the energy of the neutron is large. Okay, so in that sense the fission cross section get reduced if you increase that energy. But there is one more thing that I have to say. When you consider that uranium 238, when you consider that uranium 238, I'll just do that. So uranium 238 curve, which is going like this, you can see from here, it is starting from here and it is going like this. So this is that uranium 235, like this, something like that. And uranium 238 is here. That is the second curve. This one. This way I am saying. So this one is for uranium 235, 288. So it is starting from around 10 raised to 5, and it is having an average of 10 raised to minus 6, sorry, 10 raised to 6 value, that energy I am saying. So neutron with the 10 raised to 6 or 10 raised to 5, which is that mega electron volt range, is required for uranium 238 to have some noticeable cross section, fission cross section. So fission cross section for uranium 238, if you consider, and that fission cross section is 0 when you consider any region below this that mega electron volt or 10 raised to 5 electron volt range. Okay, you can see that this curve is starting from here only, 10 raised to 5. From here only it is starting. So in this region, this much of energy region, there is no cross section, no fission cross section for uranium 238. Uranium 238 cross section, fission cross section start when the energy reaches beyond that 10 raised to 5 electron volt. Okay, and when it reaches around 10 raised to 6 electron volt of energy, that neutrons which are having energy in the range of 10 raised to 6, this is in electron volt, then which means that around 1 mega electron volt of energy, then that will show around 10 raised to minus 1 to 1 fission cross section, on 1 to 1 fission cross section. So then it is increasing. So for uranium 238, the fission cross section starts when the energy of neutrons become 10 raised to 5 electron volt or around mega electron volt range. Okay, so for uranium 235, we have a decreasing fission cross section when you increase that neutron energy. But for uranium 238, we need at least 10 raised to 5 electron volt, or the energy we need at least in the mega electron volt range in order to have some significant amount of the fission cross section. Then only that fission happens. Then only fission starts in uranium 238, because beyond this, below this energy, the fission cross section for uranium 238 is 0. So it will not undergo fission. Okay. So fission will happen for this uranium 238 only when this 10 raised to 5 electron volt energy of neutron is absorbed by the uranium 238 nucleus. Okay. So that is the first thing, that is the scattering, fission cross section. When you consider that fission cross section, we have to, we can conclude that in this way. So for uranium 5, I'll just write it here. So for uranium 235, you can see that the fission cross section decreases. Fission cross section decreases when the energy of neutrons, in which I should say that um, just write neutrons here. The energy of neutrons. So this is for uranium-235, the fission cross-section decreases when the energy of neutron increases. So I should say as the, I should write here as. Okay, then we discussed that regions, different regions in that curve, and this is the conclusion of that figure that we discussed here. And then for uranium-238, uranium-238, reduce the thickness. Okay, for uranium-238, the fission cross section is 0. We can say very small. Okay, almost, we can say almost 0. Below few mega electron volt energy range. So I'm just giving you some kind of hint here. So this is you have to improve these sentences because here you can write 10⁵ electron volt around that range. Okay, you can elaborate that into a paragraph. These 2 points. Okay, by using that figure. I'm just giving you the conclusion or the final points. Okay. So for that uranium-238, we need at least some few mega electron volt to start that scattering fission cross section. Okay, below that the scattering cross section, sorry, fission cross section is 0. Okay, and you can say that for this particular case, uranium-238, so then we required high energy neutrons to have these fission reactions. So that was the idea behind that. So when you consider this expression, we may thought that when you increase that neutron energy, it may leads to high probability for that nuclear fissions to happen, but that is not the case. When you increase that neutron energy, the fission cross section gets reduced, and it will cause decreasing probability for the fission reaction when you increase that energy of neutrons for uranium-235. So from that curve, we can easily observe that for uranium-238, we need at least some few mega electron volt or 10⁵ electron volt of range of energy for the incoming neutrons. Okay, then only that uranium-238 undergoes this fission reaction. So those are the 2 important conclusions that we can get from that figure. And when you write it in your notes, you have to write it all those points we discussed in from that figure. Okay. So for uranium-235, you can also say in this line you can say for uranium-235 around 10 to the power -2 to 10⁻⁻1 range of energy. We have the fission cross section, which is in between 10⁻²² to 10⁻³ and say an average of this you can write average value 580 bonds, etc. So these things we discussed already. So the first section that I am saying for thermal neutrons, we have around 580 or 600 bonds that we already discussed here. Okay, so that region is then you discuss this region when you increase that thermal neutron energy beyond that thermal energy. Then you have again decreasing that fission cross section. and you have some resonance region which is showing some up and down in that fission cross section, and then again it is decreasing when you increase that neutron energy. So all these points you just note it down. Okay, so apart from this cross section, that is fission cross section, we have another important factor, that the nucleus may absorb these neutrons but will not undergo fission reaction. Okay, so what we discussed here is that this particular neutron, which is absorbed by uranium 235 and become excited, okay, and then it will convert into different nuclei. It will split into different nuclei plus some number of neutrons. Okay, so that is the fission action that is happening. But in some cases, if you have one neutron, this will be absorbed by some nucleus. Okay, let's say uranium 235 or uranium 238. In general, I am just writing U. So this can go to some excited state level, but instead of giving that fission process, it can be some other nucleus also. When it absorb this neutron, it will become mass number will be higher. So I will just represent it as U dash. Okay, then it will become U dash star, that is in the excited state. But that again will become U dash plus some gamma radiation. So these are the gamma radiation which are absorbed, which is having energy which is provided by this neutron absorption. So this neutron get absorbed into this particular nucleus, and that is going to the excited state with some different configurations, different mass number. And when de-excitation happens, then it is de-excited into its ground state, U dash, okay, by emission of some photons, that is gamma radiation. Okay, this can also happen, and this particular process which is called as when you have this absorption of neutrons but there is no fission happening, such kind of process which is called as radiative capture. Radiative capture, because in this process you will get this photons, electromagnetic radiation outside of this reaction. Gamma rays will come. Okay, photons are coming out when that excited nucleus is going to the ground state instead of giving that fission reaction. So this is also possible. This is the radiative capture process. So the neutrons are absorbed, but it will not undergo to that fission reaction, but just excite into some high energy level, then de-excite by emitting some gamma radiation. Okay, this can also possible, and this particular process is called as radiative capture. Now you look at the uranium 238 case. I will just show here. This is the diagram for that. So when you consider this particular diagram, you can see here, I will just make it more clarification. So this is 10 square. Here it is 10 cube, 10 to the power 4, 10 to the power 5, or this. And then in the x-axis, now we have a linear scale. Okay, so this is 10, then 20, 30, 40, 50, 60, etc. And just this is 60, 70, 80, 90, 20. So this is 100, right? 100, 110, 120, it will go like this. So in x-axis it is a linear scale, in y-axis it is logarithmic scale. So here you can see 10, 10 square, 10 cube. So this is logarithmic scale. Y-axis is logarithmic scale, 10, then 100, then 1000, then 10,000, like that. Okay, so it is a logarithmic scale. Y-axis is logarithmic scale. Okay, but the x-axis is in the linear scale. X-axis is linear scale. So in this also, here we have that electron volt energy. So this is nothing but energy of those neutrons. Again, energy of neutrons in electron volt. Remember, this is in electron volt. And here we have that cross section. This time, this is the cross section for neutron to get absorbed by the uh, by the that nucleus, but it will not undergo fission reaction. So this sigma that I am writing here now is the I will just write a sigma a so that it can be understood. So see, this sigma is for the cross section of absorption of neutrons. Okay, that is this sigma a, and which will not undergo fission reaction. This y-axis, which is sigma a, that is the absorption cross section for these neutrons. Okay, absorption cross section, or we can say cross section of absorption of neutrons, and which will not undergo fission reaction. So this is that sigma a. This is also in bonds. Okay, so that value is here. So then you can see uranium. This is for uranium 238. This is for uranium 238. Just increase the thickness. Okay, then you can see that for low energy, I have just shown from 10 to some 120. Okay, just remember that I'm showing from 10 to some 120 electron volt. Okay, in this x-axis, that is the energy of those neutrons. So then you can see some sharp increase in that cross section. You can see from here this curve. This is a very sharp increase in this cross section for the absorption. So this is for that absorption I'm saying. So you can see that there is a sharp increase, then it is decreasing like that. So these are not experimental result, but it is some kind of calculations that will give you some understanding how it is. Okay, so you can see that these peaks here on this is having 10 to the power 4 bonds of cross section. 10 raised to 4, this peak I'm saying. Okay, so 10 raised to 4 bonds of cross section, that is nothing but which will be equal to something like 10. Okay, this much of bonds. So it is very high cross section, absorption cross section is there for this uranium 238 when it is having energy which is very small. Okay, and you can see different peaks here all the way. You can see high cross section values for uranium 238 when you consider that energy from, for example, 10 to 120 electron volt, which is in lower energy region of in that, including that thermal neutrons, all those things. If you include that thermal neutrons also, so in this region, when the neutron energy is very small, which is not in that mega electron volt of range, then there is high absorption cross section for uranium 238, which means that if the high absorption, if there is high absorption cross section, which means that the absorption probability is very high. But from the previous curve, we can see that the fission cross section for uranium 238 in this range is very small. It is almost zero. You can see from here. From here, the in this range, or in this range of energies, you can see from 10 raised to minus 2 to some 10 square that we are considering now. So up to this 100. See, there is nothing for uranium 238. Uranium 238 fission cross section start from here, and it is going like this. Okay, so it is starting only when that energy reaches 10 raised to 5 electron volt. Okay, so below this energy, that is for when we consider now up to this 100, around 100 electron volt. So in this range of energies, we do not have any cross section, fission cross section for uranium 238. So for uranium 238, fission cross section is zero here. But when you consider that absorption cross section, you can see for uranium 238, uh, that absorption cross section is very large, 10 to the power 4 bonds. So what is happening? The uranium 238 is absorbing those neutrons with low energy, but it will not undergo that fission reaction. That's why that fission cross section is very small. It is almost zero. Okay, so the fission cross section for the uranium 238 with very low energy neutrons are zero, almost zero. So but when you consider that absorption cross section for uranium 238, it is very large for very low energy neutrons, which means that it is absorbing low energy neutrons. The probability of getting absorbed by the uranium 238 for that low energy neutron is very large, but it will not give you that fission reaction. It will just go to that excited state and de-excite by emission of that gamma radiations. Okay, so now even that thermal neutrons are getting absorbed by this uranium 238, it will not produce the nuclear fission, but just excite, and then it will de-excite and produce the ground state nucleus. Okay, so this is also possible along with that fission cross section that we considered in the just before. Okay, so that is another important physical what we say called behavior, which we can observe in this nucleus, uranium nucleus. They absorb these neutrons, but will not undergo this fission reaction. And this particular process that we call as radiative capture. Okay, so that I will just write here that point. So what we just discussed for the absorption coefficient, or the case of absorption coefficient that I am saying, absorption scattering. So okay, absorption cross section for uranium 238 nucleus is zero. Sorry, the absorption coefficient is very large. Zero. Is very large when the incoming neutrons are having low energy. So if the incoming neutrons are having very low energy, then the absorption cross section is very large. Okay, but you can say, but the fission cross section is almost zero for that case. You can write it as zero itself. When you consider that figure, you can see in the first figure there is nothing. So if you go beyond this line, only it will come. So you can say 10 raised minus 3, 10 raised minus 4, all those things. So it is almost zero. Okay. So this is this, but the fission cross section is almost zero for low energy neutrons. You can rewrite these sentences. I am just giving you some hint how to write these conclusions. So when you have that absorption cross section, if you consider that absorption cross section for uranium-238, you will be having very large value of absorption cross section when the neutron is having very small energy, very low energy. Okay, so if the incoming neutrons are low energy neutrons, then the absorption cross section for uranium-238 is very large. But still, the fission cross section for those low energy neutrons, okay, that will be very small. So in this particular case, in this I'm just writing this. So in this kind of situation, the nucleus absorb neutrons, but they will not undergo fission reaction. This phenomena is known as radiative capture. So this is called as radiative capture. So the neutrons will get absorbed, but it will not undergo that reaction. Okay, so when you consider that for the same kind of phenomena for uranium-235, that is not visible here. So here it is there. So this symbol is this. For I just write here uranium-235. For uranium-235, this cross section, that is absorption cross section, or I can say the radiative capture will be having this radiative, this for this uranium-235 radiative capture the radiative capture is having what is that cross section, which is equal to 97 bond, which is around 97 bonds. Then it gradually decreases. So for uranium-235, I'm saying, so it is around 97 bonds. So in both cases, for you consider that uranium 235, that cross section, this cross section I am saying, so that absorption cross section, or you can say that radiative capture cross section corresponding to that radiative capture process, that is 97 bonds. You can see that is for in this uranium 238, it is around this 10,000 bonds here, but it is only 97 bonds for uranium 235. So from that uranium for uranium 235 from 97, then then it decreases. Okay, after 97 bond is the low energy region cross section for this radiative capture. I can also say that. So 97 bonds is for that radiative capture. Then it will decrease when you increase that energy. Then it will again also for radiative capture also it is getting decreased. Okay, for both case, for radiative capture cross section or absorption cross section, as well as the fission cross section, both are decreasing when you increase that energy for uranium 235. Okay, so it is having only 97 bonds. So what that means is that the probability for radiative capture in uranium 235 is very small in that low energy region. So in the lower energy region, when you consider uranium 235, it is having only 97 bonds for the radiative capture cross section, absorption cross section. That means that the uranium 235, that probability to undergo through that radiative capture is very small as compared to uranium 238. Okay, because uranium 238 is having higher radiative capture cross section. Okay, that is just this absorption cross section that I was just discussed. So that is higher for uranium 238, this radiative capture process as compared to uranium 235, especially in that lower energy. Because in lower energy region, in thermal energy neutrons, for thermal energy neutrons, the fission cross section for uranium 235 will be larger, and it is around, I already discussed, which is around 580 bonds. So it is much larger as compared to uranium 238. So uranium 238 is having very small value for that low energy region fission cross section. Just this is just inverse to each other. Okay, in the lower energy region. Okay, so the radiative capture process will be very weak in uranium 235 as compared to uranium 238 in lower energy neutron. Okay. So in those cases, for example, when you have that radiative capture, radiative capture, yes, radiative capture process, when you have that radiative capture process, then the nucleus will get excited and it will just give you that gamma rays. It will not undergo fission reaction. And one more thing which will come with this is that elastic and inelastic scattering that also contribute in this fission reactions. So how the neutrons are coming and whether it is scattered from that nucleus, that also you have to include in these calculations. So this is also going to affect. Okay, so I will just put it here as a point. So we are not going to into deep of that, but just give you that there can be some elastic and inelastic scattering. There can be elastic or inelastic scattering of neutrons. Uh, from this uranium nucleus. So that also we have to consider. So if you send some number of neutrons, all the neutrons will not get absorbed by the nucleus, uranium nucleus. uh, what we discussed that as far as now is that these neutrons are getting absorbed, and that nucleus will go to excited level, then fission happens. That is the first one. Then some cases these neutrons will get absorbed, but fission will not happen, just de-excitation will happen to the ground state, and which will emit the gamma radiation. That is the second one. And in some cases, these neutrons may not get even absorbed, but just scattered by this nucleus. And the neutrons that can be elastic or inelastic scattering. So this neutron comes and just hit on that nuclear regime and just scattered from that nucleus, like the alpha particle scattering experiment. It is these neutrons can also get just scattered elastically or inelastic scattering. So that is also possible. Okay, that is also possible in this type of reactions. So that is also just I'm just mentioning that it is also possible in these reactions. Okay, so these are the basics of uranium nuclear fission processes, nuclear fission process with uranium. So these things you keep it in mind, whatever we discussed in the last class and this class, that is important for uranium fission processes.